A star is dying, yet it refuses to end its story. This is the strange physics of stellar collapse that simply does not happen. Some massive stars reach the end of their life and, against all known laws, resist the final transition into a black hole. This cosmic defiance challenges everything we thought we understood about gravity and matter. By the end of this journey, you will grasp the profound forces allowing stars to avoid that final transformation. We will uncover how quantum pressure can create an unbreakable support and what role invisible dark matter might play. How does the universe hide such deep secrets in plain sight? Deep within a vast, swirling cloud of gas and dust, a star is born. This nebula acts as a cosmic nursery, where gravity slowly and patiently pulls the scattered particles together. Over immense stretches of time, this gathering becomes a dense, hot core. When the pressure and temperature at the heart of this core become unimaginably intense, a miraculous process ignites. Nuclear fusion begins, transforming hydrogen into helium and releasing the tremendous energy that makes a star shine. For a star like our own Sun, this is the beginning of a long, stable life, one lasting billions of years. It exists in a perfect, delicate balance. The immense force of gravity constantly tries to crush the star inward, while the powerful outward pressure from the fusion reactions at its core pushes back, creating a cosmic standoff. This equilibrium defines a star's main life, but nothing lasts forever. Eventually, the star begins to exhaust its primary fuel, the hydrogen that powers its core. For a truly massive star, many times larger than our Sun, the end is far more dramatic. It starts fusing heavier and heavier elements, from helium to carbon and oxygen, and onto iron. Yet iron is a dead end. Fusing iron does not release energy, it consumes it. In an instant, the star's central support system vanishes. The outward pressure from fusion simply winks out of existence. With nothing left to fight the relentless pull of gravity, the star's core is doomed to collapse. In a typical scenario, this collapse is catastrophically fast, resulting in a spectacular supernova explosion that can outshine an entire galaxy. What remains is often an incredibly dense neutron star, or, if the core is massive enough, the formation of a black hole, a region of space where gravity is so strong that not even light can escape. This is the standard, expected fate for a massive star. Yet, as we are discovering, the universe loves a mystery. Some stars, for reasons we are only beginning to comprehend, refuse to follow this script. They reach this precipice of total collapse, but instead of falling into oblivion, they stop. Something holds them up, an unknown force that defies the most fundamental laws of physics as we know them. To understand just how bizarre and extraordinary this is, we must first appreciate the standard journey. That established path makes the defiance of these rare stars all the more shocking and compelling. The heart of a fading star becomes a stage for the most fundamental forces in nature. When gravity overpowers nuclear fusion, the core is compressed into a state so extreme that the very idea of an atom begins to dissolve. Electrons are separated from their orbits, protons and electrons are drawn together, forming a dense, swirling sea of neutrons. It is here, in this subatomic turbulence, that a quantum marvel takes place. A strange and powerful pressure arises, born not from heat or motion, but from the essential laws that guide particles themselves. This is quantum degeneracy pressure, a final, steadfast stand against oblivion. It is the universe's way of showing that matter cannot be compressed without limit. In white dwarf stars, the determined resistance of electrons provides this support. In neutron stars, it is the simple inability of neutrons to be pressed any closer that halts the collapse. For many years, we believed this quantum barrier was the ultimate safeguard. Pioneering thinkers like Subramanian Chandrasekhar worked out the precise limits of this pressure, defining the greatest mass a white dwarf could endure before yielding to gravity. Yet the cosmos is filled with exceptions. We are now observing stellar remnants, the dense cores of ancient stars that appear to exist in a stable condition far beyond these theoretical edges. They have crossed the threshold where further collapse should be unavoidable, yet they endure. Their persistence suggests that our grasp of quantum pressure is not yet complete. What if, under these extraordinary conditions, the rules themselves are being reshaped? Perhaps degeneracy pressure is not a fixed barrier, but a dynamic influence that can be strengthened or changed in ways we have not yet imagined. This leaves us with a deep question. If quantum pressure alone cannot explain this cosmic balance, what other hidden participant is joining the struggle? There is another, more dynamic force that can enter this cosmic struggle, a star's own furious spin. Think of a massive stellar core rotating at an incredible speed, its equator flung outward by centrifugal force like a cosmic whirligig. This spinning motion creates a powerful outward push, a physical counterweight to the inward crush of gravity. It is as if the star is using its own momentum to build a stabilizing wall against collapse. We see this principle in action with pulsars, the lighthouses of the universe, which beam radiation as they spin. Yet, some stellar remnants observed by powerful instruments like the Chandra X-ray Observatory spin at rates that should be impossible. According to our best models, these stars should be pulled apart by their own rotational energy, their material scattered across space, but they are not. They hold themselves together, perfectly intact, defying another set of expectations. This persistent rotation suggests that a star's spin is not just a minor detail. It can be a central actor in the drama of its final moments, a fundamental part of why some stars refuse to fade away. But rotation rarely works alone. How does this incredible spin interact with the star's immense magnetic fields, lines of force so powerful they can reshape the space around them? Could a rapidly spinning core amplify these magnetic fields to create a supporting structure, a cage of pure energy that reinforces the star? Or does the rotation work in harmony with the quantum pressure we discussed earlier, creating a hybrid defense that is far stronger than the sum of its parts? This intricate interplay between spin, magnetism, and quantum laws points toward an even more profound possibility. To achieve such a perfect, stable balance, something truly unusual must be at the heart of these stars. The answer may lie in the nature of the matter itself, a substance so exotic that it transforms our understanding of reality. Deep within these stellar furnaces, matter is pushed to its absolute limit. Under pressures and densities far beyond anything we can replicate, the familiar rules of physics begin to bend and warp. Here, the very building blocks of reality may transform into something entirely new and exotic. We call these states of matter strange quark matter or color superconducting phases, names that hint at their otherworldly nature. Imagine the neutrons in a star's core being squeezed so intensely that they themselves transform, dissolving into a sea of their most fundamental parts, quarks and gluons. This quark-gluon plasma is a primordial state, a glimpse into the universe's first microseconds. If such a transition occurs inside a dying star, it could act like a cosmic stabilizer. The process of breaking neutrons apart might release a tremendous amount of energy, creating a new, powerful form of outward pressure that gravity simply cannot overcome. This could steady the core, transforming what should have been a black hole into a new class of object, a quark star. Some of the most puzzling stellar remnants we observe, like the enigmatic RxJ 1856.53754, appear far too small and dense to be ordinary neutron stars. They fit the theoretical profile of a quark star, a sphere of pure, unconfined quark matter. This exotic substance could generate a stabilizing force so effective that it allows the star to exist safely beyond the theoretical mass limit for collapse. Yet the possibilities do not end there. In these extreme environments, matter could also form a Bose-Einstein condensate, a state where particles lose their individual identities and act as a single, coherent wave. This unified quantum state could generate a form of pressure unlike any other, a collective resistance to compression. Each of these exotic forms of matter suggests a hidden toolkit the universe uses to preserve stars that should, by all rights, vanish. But what if the strangest ingredient has yet to be considered? What if the stability of these stars is not just a matter of what they are made of, but also of what has found its way inside them? This leads us to the most elusive and mysterious possibility of all, the potential role of an invisible cosmic component. Beyond the familiar world of atoms and light, a deeper cosmic mystery permeates every corner of space. Dark matter, the invisible scaffolding of the universe, may hold the final clue to our stellar enigma. This mysterious substance does not emit or absorb light, making it impossible to see directly, yet its gravitational pull is felt on the grandest scales, guiding the motion of galaxies. What if a star, over its long lifetime, could act as a trap for this elusive material? As a massive star ages, its immense gravity could draw in dark matter particles, accumulating them in its core like a cosmic reservoir. These particles are thought to interact only very weakly with normal matter, passing through most of it as if it were not even there. But inside the star's incredibly dense heart, some might be captured, their presence building up over millions of years. This accumulation could fundamentally change the star's final act. Some theories suggest that these trapped dark matter particles could begin to annihilate with one another, releasing a steady stream of energy. This process would provide a new, persistent source of outward pressure, a hidden support system that kicks in just as nuclear fusion is failing. In this scenario, dark matter does not just add weight, it actively fights against the crush of gravity, offering a stabilizing influence that prevents total collapse. The star would not explode in a supernova or vanish into a black hole. Instead, it would settle into a new, stable form, powered from within by dark energy. Other models propose that the dark matter itself, simply by its dense concentration, could alter the local gravitational dynamics, creating a counterbalance that holds the core up. We might already be seeing the faint signatures of this process in certain stellar anomalies. Some stars in dense regions of space where dark matter is thought to be more abundant exhibit unexpected behaviors. They might shine with a steady luminosity long after their fuel should be exhausted, or they might appear cooler or hotter than our models predict. These subtle discrepancies could be the indirect clues we need, the faint whispers of dark matter's influence written in starlight. Researchers are now running complex computer simulations to test these ideas, creating virtual stars that live and die with dark matter woven into their fabric. The results are tantalizing, showing that under the right conditions, this invisible component can indeed alter a star's destiny, allowing it to defy its expected fate. This possibility connects the life of a single star to the broader cosmic environment, suggesting that where a star is born and lives its life may be just as important as how massive it is. The ultimate fate of a giant star could depend on the invisible sea of dark matter in which it is immersed. How do we search for proof of such a shadowy process? The answer may lie not in looking at the stars themselves, but in listening to the subtle ripples they create in the fabric of space-time. A star's magnetic field can be so overwhelmingly powerful it becomes a physical entity in its own right. Picture a force field trillions of times more intense than the one protecting our planet. A web of energy so dense it can actually twist the structure of atoms and bend the paths of light itself. We see the most extreme examples of this in Magnetars, where the magnetic field is strong enough to fracture the star's solid crust, triggering immense starquakes that release vast bursts of radiation across the galaxy. But for a select group of aging stars, this incredible magnetic force may serve a far more peaceful and vital purpose. It could be weaving a permanent magnetic cushion, a supportive architecture that physically props up the star against its own immense weight. This is not a gentle support, it is a fundamental restructuring of the space inside the star, creating a rigid framework that gravity simply cannot crush. Observations from space-based observatories like the Fermi Gamma Ray Space Telescope have detected stellar remnants with magnetic fields that defy our basic expectations. According to our models, fields of such staggering strength should be inherently unstable. They should tear themselves apart or fade away in a cosmic instant, yet these stars shine on, perfectly stable for millennia. Their enduring existence suggests that these magnetic fields are not decaying, they are being actively and dynamically sustained. The question is how. The answer might lie deep within the star's churning heart. A powerful internal dynamo, driven by the complex motions of superheated, electrically conductive matter, could be constantly regenerating the magnetic field, much like the dynamo inside our own planet creates Earth's magnetic field, but on an almost unimaginable scale. This would create a self-sustaining cycle, a feedback loop of magnetic energy that perpetually reinforces the star's defense. Alternatively, the influence could be external. A star drawing material from a companion star could be funneling fresh fuel and angular momentum into its core, stirring the internal motions and supercharging the magnetic dynamo. This interplay between rotation and magnetism is crucial. A star's rapid spin can stretch and amplify magnetic field lines, weaving them into a tighter, stronger web. The magnetic field, in turn, can help regulate that spin, transferring energy and preventing the star from flying apart. It is a delicate cosmic dance between three titanic forces: gravity, rotation, and magnetism, and when they find a perfect balance, the result is a star that should not exist. To unravel this mystery further, we must look to the echoes of stars past. The remnants of historical supernova, vast clouds of expanding gas and dust, hold preserved clues within their structure. The shape and distribution of elements in these clouds can tell a detailed story about the magnetic fields that were present in the star at the moment of its final transformation, or in the case of our mysterious stars, the moment it refused to fade away. By studying these ancient celestial markers, we can begin to understand how magnetic fields sculpt the final stages of stellar life. But if magnetic fields, exotic matter, and dark matter can all potentially prevent a collapse, how do we ever get black holes at all? What subtle tipping point in this cosmic balancing act leads to one star enduring while another departs from reality completely? A supernova explosion is rarely a clean, symmetrical event. It is a chaotic and powerful transition, a star transforming itself in a lopsided display. Material is not blasted outward in a perfect sphere, but is often sent forth in strong, uneven jets. This profound lack of balance might be the key to why some stellar cores resist a full collapse. As the star erupts, the immense forces involved can deliver a tremendous push to the dense remnant left behind, like a rocket engine firing from one side. This push does more than just send the core moving through space. It can also set it spinning at a remarkable rate. That sudden, intense rotation could provide just enough outward support to stabilize the core against the final pull of gravity, leaving it in a lasting state of balance. We see direct evidence of this in objects like the pulsar at the heart of the Crab Nebula. This neutron star is not resting quietly at the center of the explosion cloud. It is speeding away from the site of the supernova at over 1,000 kilometers per second, a clear sign of an imbalanced event. In the most extreme cases, this powerful off-center process might not leave behind a neutron star at all, but something even more intriguing, a star that experienced an incomplete collapse. This would be an object that began the irreversible journey toward a black hole, only to be pulled back at the last possible moment by the forces of its own dynamic transformation. The intricate structures we see in supernova remnants, captured in beautiful detail by the Hubble Space Telescope, tell this story. The twisted knots and vast, uneven lobes of glowing gas are a lasting record of that final, asymmetrical release. This invites a significant shift in perspective. What if asymmetry is not merely a side effect of the explosion, but the very process that allows a star to alter its expected path? The final outcome of a star's life may depend on the precise shape of its transformation. This line of thinking naturally draws our attention outward beyond a single, isolated star. Could the presence of a companion star be the ultimate source of this life-preserving asymmetry? A star never truly lives alone. Across the cosmos, most stars are born in pairs or small families, gravitationally bound for their entire lives. This cosmic companionship completely reshapes the final act. Picture two massive stars locked in a slow, graceful dance around a shared center. As one star ages and begins to swell into a red giant, its outer layers become vulnerable. The immense gravity of its companion star can begin to pull this material away, siphoning a stream of gas directly from one star to the other. This process, known as mass transfer, is a stellar exchange that alters destiny. For the aging star, this loss of its outer envelope is a profound transformation. It is not just losing mass, it is shedding the very weight that was destined to press upon its core. By stripping away these layers, the star might reduce the final density of its core just enough to fall below the critical threshold for collapse. Instead of imploding into a black hole, it could settle as a stable neutron star, its fate changed by its partner's pull. The influence does not stop there. As the gas spirals from one star to the other, it does not fall straight in. This incoming material carries immense angular momentum, striking the receiving star like a constant, sideways push. This can dramatically spin up the star, setting its core rotating at a remarkable speed. That rapid rotation, as we have explored, creates a powerful centrifugal force, building a structural support against gravity's inward press. In this way, a binary companion does not just take mass, it can give the gift of spin, providing a second mechanism to prevent a total collapse. We see echoes of this intricate dance in the data from gravitational wave observatories like LIGO. The signals from merging binary neutron stars tell us that these incredibly dense objects were once stars in such a system. Their very existence and their ultimate convergence is a direct result of this complex binary evolution. They did not form in isolation, and they did not collapse alone. Their unusual fates were written by their partnership. In even rarer scenarios, this transferred mass can act as a temporary revival. A white dwarf or an aging giant approaching its final transition can accumulate so much fresh hydrogen from its companion that it reignites nuclear fusion on its surface. This triggers a tremendous outburst, a nova, that blasts away the accumulated material and fundamentally resets the star's internal clock. While this might only delay the inevitable, it is a stunning demonstration of how a stellar partnership can intervene at the last possible moment. This raises a compelling question. Just how common is this binary influence? Current estimates suggest that over half of all stars are in multi-star systems, meaning the unusual fates we are exploring might not be rare exceptions at all. They could be the standard outcome for a huge portion of the stellar population. Our own Sun, a solitary star, might be the cosmic outlier. This realization forces us to look beyond single-star models and into the complex theoretical frameworks that simulate these dynamic duos. These models show that mass transfer and tidal forces can produce a menagerie of exotic objects that would never form in solitude. The universe seems to prefer its stars to have company, and that company often determines whether a star will fade away or defiantly endure. Subramanian Chandrasekhar gave us a beautiful and precise boundary, a line drawn in the sand of the cosmos. He calculated that a white dwarf star, the dense Earth-sized core left behind by a Sun-like star, could not support itself if its mass exceeded about 1.4 times that of our Sun. Beyond this Chandrasekhar limit, the quantum pressure from its electrons should fail, and gravity should force a profound transformation into a neutron star or a black hole. For decades, this was a cornerstone of astrophysics, an unshakable rule, but the universe has a habit of challenging our most elegant ideas. Astronomers have now found white dwarfs like the one known as SDSS J0822+2753 that are far more massive than this limit, yet they show no signs of transforming. They simply exist stable and serene in a state that should not be possible. How can this be? The answer seems to lie in what Chandrasekhar's original, elegant calculation left out. His model considered a perfect static sphere of matter. Real stars are far more dynamic. What if the star is spinning rapidly? That rotation creates a centrifugal force that effectively lightens the core, allowing it to hold more mass without immediately changing form. It is like a spinning ice skater who can hold a difficult pose because of their momentum. The composition of the star matters too. A white dwarf rich in oxygen and neon might behave differently under extreme pressure than one made mostly of carbon and oxygen, potentially altering the point at which fusion could reignite. Then there is the staggering power of magnetic fields. Some of these massive white dwarfs possess magnetic fields of immense strength. This magnetic energy might provide additional structural support, creating an invisible scaffold that reinforces the star against its own weight, effectively raising the mass limit for transformation. This is not a minor oversight, it is a fundamental challenge. The existence of these stars invites us to ask whether the Chandrasekhar limit is a fixed constant of nature or a flexible boundary that depends on a star's individual history, its rotation, and its magnetic character. Experts actively discuss whether thermal effects from residual heat or sudden flashes of fusion could provide a temporary support, allowing the star to exist beyond the limit for a short cosmic moment. Each of these exceptions opens a deeper question about the very constants that underpin our physical models. If a number we thought was universal can be flexible, what else about our understanding is still taking shape? This puzzle inevitably draws us toward an even more profound force, one that becomes dominant in these extreme environments. To truly grasp why some stars remain stable, we must venture into the warped geometry of spacetime itself, where general relativity takes center stage. Einstein's theory of general relativity shows us that gravity is not a simple pull, but a bending of the fabric of spacetime itself. Near a massive, rapidly spinning stellar core, this curvature becomes something extraordinary. The star's immense rotation does not just move through spacetime, It actively pulls the fabric along with it, twisting the very coordinates of reality in a process known as frame dragging. Imagine a heavy ball spinning in a thick fluid, pulling the surrounding liquid into a whirlpool around it. In the same way, a dying star can entrain the spacetime around it, creating a cosmic vortex that generates additional forces. These forces are not electromagnetic or nuclear, they are purely geometric, born from the warped geometry of the universe. In an object like a theoretical Kerr black hole, frame dragging becomes so extreme it creates a region called the ergosphere, where nothing can remain stationary. It is forced to rotate with the black hole. For a star that has narrowly avoided collapse, this frame dragging might not reach such extremes. Instead, it could settle into a perfect, balanced state. The dragging of spacetime could produce an effective outward pressure, a relativistic reinforcement that helps the star resist the final, crushing grip of gravity. It would be like a spinning top that uses its motion to stabilize against falling over, but here, the motion is twisting the stage on which it stands. We may already have observational hints of this phenomenon. Some dense stellar remnants are orbited by companion objects whose paths slowly precess or wobble over time. This precession is more than what standard gravity predicts. It is a subtle signature written in the language of general relativity, a clue that the central star is not just massive, but is actively churning the spacetime around it. Untangling these effects requires venturing into the complex mathematics of Einstein's field equations, a realm where time and space are interwoven and dynamic. This deep connection between rotation and spacetime naturally leads us to consider an even more elusive process. If a star's gravitational field is this powerful, could it also interact with the quantum fields that pervade the vacuum of space, perhaps giving rise to radiation that slowly saps its energy over cosmic timescales? The vacuum of space is not truly empty. Even in the deepest voids, it seethes with a hidden energy. Quantum fields constantly flicker, giving rise to virtual particles that appear and vanish in a spontaneous, unpredictable dance. Under normal conditions, this quantum activity is a subtle background hum, its effects incredibly small, but inside the immense density of a fading star's core, this faint hum could become a powerful presence. The sheer pressure might be enough to bring these quantum field fluctuations into the open, transforming them from a theoretical idea into a tangible, physical influence. One possible mechanism is an effect we can observe in laboratories here on Earth, the Casimir effect. When two perfectly smooth metal plates are placed extremely close together in a vacuum, the quantum fluctuations in the space between them are limited. This creates a subtle but measurable pressure that draws the plates together. Now imagine the reverse. Inside a star, the geometry is not one of plates being pushed together, but of a dense sphere where the quantum fluctuations outside differ from those within. This difference could, in theory, generate a net outward pressure, a quantum nudge against gravity's inward pull. This would not be a force born of heat or spin, but from the fundamental nature of empty space itself, amplified to a cosmic scale. Some theoretical models propose that under these specific, extreme conditions, these vacuum effects could become the main form of support, creating what is known as a quantum-supported star or an electrovacuum star. In this scenario, the star is not held up by neutron pressure or exotic matter, but by the constant, vibrant energy of the quantum vacuum. Its stability would be a direct result of the universe's most basic rules unfolding on a grand stage. This speculative idea reaches beyond stellar physics and touches upon one of the greatest mysteries in all of science, the nature of dark energy. The same vacuum energy that might hold up a single star is also thought to be causing the accelerated expansion of the entire cosmos. Could these two phenomena be different expressions of the same underlying quantum reality? How could we possibly test such an abstract and delicate concept? The challenge is immense, as the signals would be incredibly faint. One approach is to look for the unique gravitational signature such an object would produce. A quantum-supported star would have a density and structure subtly different from a neutron star or a quark star. As it rotates, the tiny ripples in spacetime it generates, its gravitational waves, would carry a specific fingerprint. Next-generation gravitational wave observatories, with their remarkable sensitivity, might be able to detect these quiet whispers and distinguish them from the signals of more familiar objects. Another method involves studying the star's cooling process. A star powered by vacuum energy would lose heat in a way that differs from the standard models for neutron star cooling. By carefully measuring the temperature of old, isolated stellar remnants over long periods, we might notice the subtle signs of this quantum process at work. The search for this evidence is a profound journey, one that connects the story of a single, enduring star to the deepest principles shaping all of reality. A star's final act is written in its chemical signature. The elements forged in its heart and inherited from its birth cloud set the stage for its ultimate defiance. This hidden factor, known as metallicity, refers to the abundance of every element heavier than helium. Carbon, oxygen, iron, and even trace amounts of gold and uranium are all considered metals in the language of astronomy. A star born with a rich supply of these materials behaves fundamentally differently at the end of its life than a star born from almost pure hydrogen and helium. The presence of these heavier elements increases the star's opacity, making its interior more like a dense fog. This slows the escape of radiation, changing how heat flows from the core to the outer layers and reshaping the entire internal structure of the star. This altered structure can create a more diffuse, layered core that is less prone to a single, dramatic failure. The outcome is not always straightforward, however. In some metal-rich stars, these same heavy elements can act as catalysts, accelerating certain fusion processes and leading to a more rapid consumption of fuel. This can cause the core to produce a tremendous flood of neutrinos, those ghostly particles that barely interact with matter. In a staggering cosmic trade-off, this neutrino wind can carry away vast amounts of the core's energy in a final, silent exodus. This energy loss might sap the strength of the eventual supernova event, leaving behind a remnant that is less compressed and more stable, a star that narrowly avoids the final transformation. We see compelling evidence for this in the crowded stellar hubs at the centers of galaxies. Here, stars are often born from gas enriched by countless previous generations of supernova, making them exceptionally metal-rich. Within these glittering metropolises, we observe a wider-than-expected variety of stellar fates. Some stars explode as predicted, while others seem to simply wink out, leaving behind stable remnants that should not, by standard models, exist. Their survival appears directly linked to their unique chemical makeup. This variability forces us to ask a deeper question: could specific, rare elements be the key? Elements like radioactive thorium or uranium, present in only minuscule amounts, release energy through their slow decay over billions of years. In the extreme environment of a stellar core, this steady, low-level heating might provide just enough additional pressure to tip the balance against gravity. The star becomes a natural nuclear reactor, its longevity assured by the slow burn of its heaviest elements. This intricate dance of chemistry and physics is also the origin story for every heavy atom in the universe. The very elements that might allow a star to resist collapse are the same ones forged in the hearts of stars that did collapse. A metal-rich star that refuses to become a black hole becomes instead a prolific factory. Its stable, prolonged existence allows it to synthesize vast quantities of heavy elements through slow neutron capture processes. When it finally does shed its outer layers, it seeds the surrounding cosmos with the building blocks for rocky planets and ultimately life. The iron in your blood and the calcium in your bones were likely created in a star that, against all odds, chose to endure. This profound connection ties our own existence to the most stubborn stars in the cosmos. How do we begin to map this incredible chemical diversity across the galaxy? The answer lies in reading the starlight itself, deciphering the subtle spectral lines that act as a star's unique fingerprint. These ghostly particles emerge in a frantic, final burst as a star collapses. Neutrinos are so elusive that trillions pass through your body every second without a trace, yet in a supernova, their numbers are beyond comprehension. For a brief, incredible moment, the energy they carry away can exceed the combined light of every star in the galaxy. This rapid cooling is typically what allows gravity to finalize its work, removing the core's last source of support. But what if this process is not quite perfect? Imagine a crowded room where everyone tries to leave at once through a single, narrow door. The exit becomes a chaotic bottleneck, and the pressure inside the room builds. Inside a dying star, a similar traffic jam could occur. If the neutrino flux becomes inefficient or uneven, these particles might not escape cleanly. Instead, they could become temporarily trapped, interacting with the dense matter in the core. This trapped sea of neutrinos would exert its own outward pressure, a final, fleeting support system born from the very process meant to seal the star's fate. It would be akin to how radiation pressure supports a young star, but here, the supporting force is built from ghostly particles in their final moments. Experiments like the Super Kamiok and detector in Japan have given us glimpses of this delicate process. This immense underground chamber filled with ultra-pure water has captured neutrinos from distant supernova, but the data holds subtle puzzles. The arrival times and energy profiles of these neutrinos sometimes deviate from our simulations. They suggest that the neutrino flow is not a simple, smooth exodus. It might be staggered or redirected by powerful magnetic fields, creating an asymmetry that leaves pockets of residual heat within the core. This leftover warmth could be just enough to tip the balance, providing the crucial margin that allows a star to resist complete collapse. This intricate interplay between neutrino physics and gravity points toward an even more profound transformation happening at the heart of the star. The intense pressure and the altered energy flow could be triggering a fundamental shift in the state of matter itself, a phase transition that solidifies the core's enduring nature. Deep within the heart of a dying star, the very essence of matter can shift its fundamental state. This is a phase transition, an event as profound as water freezing into ice, but occurring under pressures that reshape atoms into entirely new forms of existence. The core, under this immense strain, does not simply compress, it transforms. One of the most compelling possibilities is the formation of superconducting nuclear matter, a state where protons and neutrons pair up and flow without any resistance at all. This sudden reorganization releases a tremendous burst of latent heat, a final surge of energy from the changing nature of matter itself. It is a cosmic reprieve, a thermodynamic gift that can push back against gravity's relentless pull, effectively halting the collapse in its tracks. This process is not merely theoretical, it is mapped on something known as the QCD phase diagram, a complex chart that physicists use to predict how nuclear matter behaves under extremes of temperature and density. The path a star's core takes across this diagram determines its ultimate fate. A core that passes through a specific critical point might undergo a gentle transition into a quark star, where neutrons dissolve into a soup of their fundamental components. This new state of quark matter could be remarkably stable, creating that perfect intermediate object, neither a neutron star nor a black hole, but something enduringly in between. The trigger for such a profound change is incredibly subtle. It depends on the exact balance of density, temperature, and even the precise chemical composition we discussed earlier. A slight variation in any of these factors could mean the difference between a sudden phase transition that stabilizes the core and a continued descent into finality. This intricate thermodynamic puzzle connects directly back to the long history of stellar observation. For centuries, we simply classified stars by their color and brightness. Now we are learning that their most profound secret is written in the hidden physics of their final moments, in the silent, universe-altering shift from one state of being to another. What other invisible transformations are occurring within these stellar furnaces, and how can we hope to detect them from across the vastness of space? Centuries-old star charts hold secrets we are only now beginning to decipher. When the brilliant Tycho star appeared in the constellation Cassiopeia in 1572, it shone brighter than Venus, visible even in the daytime sky. Astronomers of the era meticulously recorded its sudden appearance and gradual fade, but the true mystery was left for modern science to uncover. When we point our most advanced telescopes at the remnant of that very event, we find a puzzling structure. The cloud of expanding material is oddly shaped and contains pockets of elements in concentrations that do not align with a standard, symmetrical core collapse. This suggests the original star may not have experienced a clean, total implosion. Instead, it might have undergone a partial transformation, leaving behind a stable remnant that has since faded from view, its existence inferred only by the chemical echoes it left behind. This is not an isolated case. Modern sky surveys like the Kepler mission, which stared unblinkingly at vast star fields, have recorded other unusual behaviors. Some massive stars exhibit faint, rhythmic dimming long after their main sequence life should be over, as if an internal structure is shifting and settling. Others flare with unexpected brightness, not from a surface event, but from a deep, internal release of energy. These are not the final moments of a star giving in to gravity. They are the signs of a star holding on, finding a new balance against all odds. These historical and modern anomalies invite a profound shift in our perspective. For decades, our models of stellar evolution have assumed a certain uniformity, a predictable end-game dictated solely by mass. But the universe, it seems, prefers a more diverse and creative set of outcomes. The long-term record written in the sky tells us that non-collapsing stars are not fantastical exceptions. They are a recurring feature of the cosmic landscape, their stories woven into the historical fabric of astronomy itself. By carefully re-examining these ancient observations alongside contemporary data, we can begin to trace patterns across time. Does a star's location in a metal-rich galactic region make it more likely to avoid collapse? Could the presence of a binary companion, inferred from subtle orbital clues in historical brightness records, be the hidden factor that allows for stability? Each historical anomaly is a piece of a much larger puzzle, offering a unique long-term dataset that our brief human timescales could never provide. What other clues about stellar endurance are waiting to be rediscovered in the forgotten observations of the past, and how will they reshape our simulations of the future? Even our most powerful supercomputers can only offer a simplified sketch of a star's final moments. These simulations are marvels of modern science, crunching numbers for millions of virtual hours to model a process that takes mere seconds in reality. Yet they operate with built-in limitations, forced to assume a perfect, smooth, and symmetrical star, a celestial body that simply does not exist in the dynamic cosmos. Real stars are churning with immense turbulence, crisscrossed by powerful magnetic fields, and shaped by deep-seated asymmetries that our current models struggle to represent with full accuracy. When researchers like Stan Woosley run these digital experiments, they sometimes witness a startling outcome. By subtly adjusting a single parameter, such as the star's initial rotation rate or the precise mix of elements in its core, the virtual star can defy its programmed fate. The simulation, designed to produce a black hole, instead shows the core rebounding, settling into a stable configuration that should be impossible. This is not a programming error, it is a clear signpost pointing toward the gaps in our fundamental knowledge. These digital stars are refusing to collapse because our equations are missing a crucial piece of the puzzle, an unknown variable or a misunderstood interaction. The turbulence we overlook might be generating a hidden form of pressure. The magnetic fields we simplify could be weaving a supportive structure we have not yet quantified. How do we move from these elegant approximations to a truer picture of stellar transition? The path forward is driven by a cycle of discovery. Each puzzling simulation result underscores our profound need for more real-world data. This urgent need, in turn, fuels the development of the next generation of observational technology, pushing us to build instruments that can finally peer into the heart of the mystery. Every ripple in spacetime carries a unique signature. When two black holes spiral into each other, they send out a specific, rising chirp before falling silent. The collision of two neutron stars produces a different kind of signal, one often accompanied by a flash of light. But what of the stars that refuse to collapse? Their gravitational whisper would be unlike any other. Instead of a final, catastrophic crash, we might detect a steady, continuous hum, a low-frequency tone generated by the stable oscillations deep within their cores. These subtle vibrations are the star's way of ringing like a bell, and the frequency of that ring would tell us everything about its internal structure and the mysterious forces holding it up. No such signal has been definitively identified yet, but the theoretical search is already underway. Scientists are creating libraries of predicted waveforms, modeling what the gravitational echo of a quark star or a magnetically supported object would sound like. The key is in the details. The frequency and amplitude of these continuous waves would be a direct probe into the star's density, its rigidity, and the equation of state of the exotic matter that might compose it. A star supported by a Bose-Einstein condensate would vibrate differently than one held together by a powerful magnetic cage. We would, for the first time, be able to listen to the heart of these cosmic enigmas. The search for these whispers is not limited to isolated stars. When observatories like LIGO and Virgo detect the merger of two neutron stars, the properties of the resulting remnant are encoded in the final moments of the signal. Does the merged object immediately collapse into a black hole, or does it persist, stable and defiant, for even a fraction of a second longer than our models predict? That brief delay, that extra ripple in the data, could be the first indirect evidence of a stabilization mechanism at work, a hint that the new object found a way to endure. This quest represents the cutting edge of multi-messenger astronomy. It is the practice of combining different forms of cosmic intelligence. A continuous gravitational hum from a nearby, non-collapsing star, if ever detected, would trigger a global campaign. Radio telescopes would turn to listen for pulsations. X-ray observatories would measure its surface temperature. Optical telescopes would analyze its light. By layering all these observations together, we could build a complete portrait of a star that should not exist, understanding it not through a single sense, but through a symphony of them. What other secrets about the fundamental nature of matter and gravity are waiting to be heard in the quiet vibrations of the cosmos? A single type of observation gives us only a fragment of the story, like hearing one instrument from a grand orchestra. The true harmony of a star's final moments is revealed only when we listen with every sense we possess. This is the power of multi-messenger astronomy, a discipline that weaves together different strands of cosmic information into a single, rich tapestry. We combine the faint ripples of gravitational waves with the brilliant flash of gamma rays, the steady glow of X-rays, and the ghostly passage of neutrinos. Each messenger carries a unique piece of the truth. Consider an ultra-luminous X-ray source, a celestial object shining with the power of millions of suns. If we observe it with an X-ray telescope, we see a beacon of intense energy. According to old models, such brilliance should come from a black hole voraciously consuming matter. But when we listen for gravitational waves, we hear no signature of a final, violent collapse. This discrepancy is a profound clue. It suggests the object is not a black hole at all, but a stable, magnetized neutron star, or perhaps something even more exotic, radiating steadily without succumbing to gravity's final call. Its internal structure must be providing a perfect, enduring support. Global collaborations are now actively hunting for these correlations. The Ice Cube Neutrino Observatory, positioned deep in the Antarctic ice, watches for the subtle signals of neutrinos from cosmic events. At the same time, the James Webb Space Telescope peers into the infrared, studying the chemical aftermath of stellar transitions. When these instruments detect an event in concert, we can match the neutrino burst with the elemental signature of the resulting cloud, building a timeline of the star's transformation. Did the neutrinos stall, providing temporary support? Does the ejected material show an unusual abundance of certain elements, hinting at a prolonged, stable fusion process in a core that refused to fade? This integrated approach allows us to see not just what happened, but how the various forces interacted. We can trace how a star's mighty magnetic field channeled its explosive energy, or how its rapid rotation created asymmetries that led to stability instead of collapse. This is how we move from simply cataloging anomalies to truly understanding the mechanics of cosmic defiance. The promise of this method is only beginning to be realized. How will future missions with even greater sensitivity and coordination deepen our view into this hidden layer of stellar physics? The James Webb Space Telescope is now turning its golden eye toward the dusty memorials of ancient stars. Its extraordinary infrared vision allows it to see straight through the cosmic clouds that have long hidden the final phases of stellar lives. Where other telescopes see only a dark veil, Webb sees the intricate chemistry and structure of planetary nebulae and the glowing traces of supernova. It is reading the light from these objects with a precision we have never had before, searching for subtle anomalies written in their spectra. An unexpected emission line here, a strange asymmetry in the shape of an expanding cloud there. These are the faint clues that could point to a core that refused to fade. Early data from the telescope has already sent ripples through the astrophysics community, presenting features around certain stellar remnants that our current models struggle to explain. Some patterns of elemental distribution suggest a far more gentle and prolonged transition than a violent core collapse should allow. The next phase of its mission could involve direct observations of candidate objects, stars that have been flagged as potential non-collapsing remnants based on their unusual X-ray or radio signatures. By analyzing their infrared light, Webb can determine their surface composition and temperature with incredible accuracy. providing the first real physical measurements of what these objects are truly made of. How will this new flood of data reshape our fundamental understanding of stellar evolution? It promises to do more than just add new entries to our catalogues. It could force us to redraw the entire chart of stellar life cycles. The very definition of a star's final state may need to be expanded to include a spectrum of stable fates, not just a binary choice between neutron stars and black holes. This continuous, refined observation ties directly into the largest questions of cosmology. If a significant number of massive stars are avoiding collapse, it changes our estimates of how many black holes exist, which in turn influences our models of galaxy formation and the growth of the universe's largest structures. Every new image from Webb is not just a picture, it is a potential key waiting to unlock the next chapter in our understanding of cosmic balance. The enduring stability of a star rewrites the cosmic ledger. For generations, we have mapped the heavens assuming a strict accounting of stellar life cycles, a predictable number of dense objects seeding each galaxy. But if a significant population of massive stars refuses to complete their final transformation, that entire calculation falls apart. The consequences ripple outward, touching the grandest scales of cosmic evolution. A universe with fewer of these gravitational anchors is a universe with a different kind of structure. These enigmatic objects are thought to sit at the hearts of galaxies, their immense influence guiding the orbits of billions of stars. With fewer of these central engines, the majestic swirl of a spiral galaxy might evolve differently, its structure perhaps looser or its central core less defined. This change in the population of stellar remnants could even subtly influence the distribution of dark matter itself. The invisible halo that cradles a galaxy responds to the gravity of the visible matter within it. If the number of ultra-dense objects changes, the dark matter might settle into a new, unexpected configuration, reshaping the very scaffolding of the cosmos. This touches upon one of the most profound questions in modern cosmology, the ultimate fate of everything. Our leading model points toward a slow, cold expiration known as the Big Freeze, where the universe expands forever, stars burn out, and even the most massive objects eventually fade over unimaginable eons. But this model relies on stars efficiently recycling their material through dramatic stellar events, seeding space with the heavy elements for new stars and the gravitational centers that govern structure. If many stars instead become long-lasting, stable remnants, that recycling process becomes less efficient. The universe might age differently. Its final chapters were written by the quiet persistence of its most massive suns. This realization connects the fate of a single star to the destiny of the entire cosmos, suggesting a deeper, more interconnected hierarchy than we ever suspected. Where does that leave us, a species living on a fragile world around an average star? The possibility that the universe is filled with these enduring celestial objects, these cosmic survivors, reframes our search for meaning and for other life. If stellar stability is more common, then planetary systems around long-lived stars have even more time for life to arise, evolve, and look back at the heavens in wonder. Our own existence is tied to the chemical generosity of stars that completed their cycles long ago. What new possibilities emerge from the stars that choose to persist? The search for extraterrestrial intelligence becomes, in part, a search for civilizations that may have arisen under the steady, ancient light of a star that refused to fade, a constant in their sky for billions of years longer than anyone thought possible. Their understanding of the universe and their place within it would be fundamentally different from our own. A star that endures for billions of years beyond its expected life does more than defy physics. It offers a permanent harbor for possibilities we can barely conceive. This remarkable stability creates an environment where the slow, delicate process of life could not only begin but flourish across cosmic timescales. The dramatic end of a typical star clears its entire system, but a star that resists collapse provides a steady, unwavering light. Its planetary system, bathed in this constant glow, would experience no such catastrophic reset. Worlds within its habitable zone would enjoy an era of tranquility lasting not for millions, but for billions of additional years, time enough for evolution to explore pathways beyond our imagination. This makes such stellar anomalies prime targets in the search for extraterrestrial intelligence. Initiatives like the Search for Extraterrestrial Intelligence, or SETI, could pivot their listening efforts toward these cosmic elders, scanning the regions around them for artificial signals. The very nature of the star suggests a long-term stability that would be invaluable for any civilization looking to the future. The ultimate energy source for an advanced society would not be a fleeting star, but one that promises to shine almost forever. Could a sufficiently advanced culture learn to tap directly into the exotic physics that sustains such a star, drawing power from its quantum pressure or its immense magnetic fields? The star itself would become their engine, a cosmic battery of unimaginable capacity. This is not merely science fiction. It is a logical extension of looking for life in the most stable and long-lived environments the universe has to offer. We might even search for signatures of this activity indirectly. An unusual infrared excess around one of these stars could hint at a Dyson sphere, a vast structure built to capture its energy output. Unexplained periodic dimming might not be from natural causes, but from immense orbital platforms. While these ideas remain speculative, they transform the search for life from a purely biological pursuit into a broader archaeological one, looking for the physical artifacts of intelligence on a stellar scale. This creative approach encourages us to see these non-collapsing stars not just as physical curiosities, but as potential cosmic lighthouses, their enduring light guiding our search for company in the vast and silent dark. Our own planet has become a testing ground for the universe's most extreme physics. Inside sprawling facilities like the National Ignition Facility, scientists use the world's most powerful lasers to compress tiny capsules of hydrogen fuel, creating for a fleeting nanosecond conditions that rival the heart of a star. The goal is to achieve nuclear fusion, but the data streaming from these experiments is a treasure trove for astrophysicists. It reveals how matter behaves under pressures and temperatures we could once only theorize about, showing us the precise moment when materials might shift into a new, exotic state. In Switzerland, the colossal particle accelerators at CERN perform a different kind of cosmic mimicry. By colliding atomic nuclei together at nearly the speed of light, they create a primordial soup of quarks and gluons, a state of matter not seen since the universe's first moments. This quark-gluon plasma is a direct analog for what we theorize exists inside a quark star. By studying its properties, its viscosity, and how it cools, we gain tangible clues about the kind of stable, exotic matter that could allow a stellar core to endure. These terrestrial experiments are not perfect replicas. They are tiny, transient, and scaled down from the cosmic reality. Yet they provide something theory alone cannot: hard, repeatable data. They allow us to test the equations of quantum chromodynamics and general relativity in a controlled environment, observing how these fundamental forces interact under intense conditions. The results so far have been both confirming and confounding. They confirm that matter does undergo profound phase transitions under extreme density, just as our models predict. Yet they also show that the behavior of this super-dense matter is far more complex and turbulent than we imagined, hinting at stability mechanisms we are only beginning to quantify. This practical, hands-on approach is vital, bridging the gap between abstract mathematics and the tangible cosmos. It transforms stellar astrophysics from a science of distant observation into one of active experimentation, bringing the mysteries of stellar evolution into the laboratory. This spirit of discovery naturally extends beyond the lab walls, inspiring a new generation to look up at the night sky and wonder what other cosmic secrets we can unravel here on Earth. The mystery of these enduring stars is no longer confined to professional observatories. An online platform called Zooniverse has opened a digital doorway, inviting anyone with an internet connection to become a cosmic explorer. This is citizen science in action, a global collaboration where public volunteers help sift through the mountains of data collected by telescopes. Your own eyes might be the first to spot a subtle anomaly in a star's light curve, a tiny fluctuation that hints at a core stubbornly resisting collapse. This is how ordinary people are making extraordinary contributions to astrophysics. We have already seen the power of this approach in projects like Galaxy Zoo, where public volunteers classified millions of galaxy shapes, and in Searches for Supernova, where amateur astronomers have helped track the fading light of stellar events. By distributing the workload across thousands of curious minds, researchers can analyze datasets that would otherwise take a single team a lifetime to process. This does more than just accelerate discovery. It builds a bridge between complex theoretical physics and public understanding. When you personally classify a star's behavior, the abstract concepts of quantum pressure and frame dragging transform into a tangible quest. You are not just learning about the universe, you are actively helping to map its deepest secrets. How can you get involved? The process is remarkably simple. You can visit the Zooniverse website, create a free account, and choose a project like Planet Hunters or Supernova Hunters. A brief tutorial will guide you on what to look for, and then you are presented with real, unanalyzed data from space telescopes. Your classifications, combined with those of other volunteers, provide scientists with the statistical power to identify the most promising celestial oddballs for further study. This collective effort embodies a profound scientific principle, the importance of questioning established theories. Every time a volunteer flags a star that does not fit the standard model, they are participating in the very essence of scientific progress. They are helping to challenge our assumptions and push the boundaries of what we believe is possible in the cosmos. This collaborative spirit ensures that the search for answers is a shared human endeavor, one where every curious mind has a role to play. History reminds us that science does not advance in a straight line. It lurches forward when stubborn facts refuse to fit our most cherished theories, forcing a revolution in thought. The quiet defiance of a star that should have faded is precisely this kind of anomaly, a cosmic nudge that could reshape our current understanding of gravity and matter. For centuries, we operated under the beautiful, predictable laws of Newtonian physics, a universe of absolute time and clear forces. Then came the strange orbits of Mercury and the bending of starlight, puzzles that only Einstein's theory of relativity could solve. Later, the unusual behavior of atoms demanded the equally surprising rules of quantum mechanics. Each of these was a paradigm shift, a complete overhaul of our cosmic rulebook driven by something that simply would not fit. Today, the star that resists its expected fate is our Mercury, our atom. It stands as a monument to the incompleteness of our knowledge, a challenge written in starlight. This healthy skepticism is the lifeblood of discovery. It encourages physicists to propose radical new frameworks, from theories of modified gravity that change how mass behaves on large scales, to the mind-bending possibility of extraspatial dimensions subtly influencing stellar cores. These are not wild guesses, they are necessary extensions of our models, born from the obligation to explain what we see. As the physicist Carlo Rovelli often notes, it is mystery, not certainty, that propels science forward. The moment we think we have everything figured out is the moment progress stops. The enduring star is a gift of mystery, a persistent question that pushes us to rethink the fundamentals of reality itself. How will solving this particular puzzle reshape our future? The implications reach beyond pure physics, touching on something far more tangible, the immense value of the resources these stellar survivors might hold. The enduring light of a stable stellar remnant represents more than a scientific curiosity. It is a potential resource on a cosmic scale. Imagine a future where humanity has mastered interstellar travel. In the vast, dark stretches between stars, these persistent objects would be invaluable. Their incredible stability makes them perfect natural lighthouses, fixed points for navigation in a sea of moving stars. A ship's computer could triangulate its position using the steady pulse of a distant, non-collapsing star, a celestial landmark that has not changed for millions of years. Beyond guidance, the star itself is a powerhouse. We already capture a fraction of our sun's energy here on Earth. A civilization advanced enough to travel between stars could conceivably build vast collectors to harness the steady, immense output of a stellar remnant, drawing power directly from its exotic physics. This is not merely about solar panels in space. It is about tapping into the fundamental forces that prevent gravitational collapse, perhaps drawing energy from the star's powerful magnetic fields or the quantum processes at its core. The materials within such an object are equally tantalizing. A quark star, for instance, would be composed of matter in a state impossible to create on Earth. Studying, or even one day carefully collecting, such material could unlock technologies we can barely envision, from new forms of energy storage to materials with unimaginable strength. This speculative leap forces us to confront profound ethical questions. Who has the right to use such a cosmic object? If a star is a potential resource, does it belong to whoever reaches it first, or is it part of a shared cosmic commons? The very act of utilizing a star, of altering its environment for our benefit, carries a weight of responsibility. It invites us to look beyond the immediate physics and consider our role as a species taking its first steps into a wider universe. How will we explore without exploiting, and how do we ensure that our reach into the cosmos is guided by wisdom as well as wonder? Our reach into the cosmos must be guided by more than just curiosity. As we contemplate sending probes to study these stellar survivors up close, a profound responsibility emerges, one that echoes the principles of planetary protection developed for our own solar system. The goal there is to avoid biological contamination, to ensure we do not inadvertently carry earthly microbes to worlds that might harbor their own fragile beginnings of life. With a non-collapsing star, the risk is not biological but physical and fundamental. A close approach by a spacecraft or a deliberate experiment designed to probe its structure could theoretically disrupt the very balance that allows it to endure. The immense energy output of our instruments, or even the gravitational influence of a probe passing too near, might be enough to nudge a delicately balanced system. It would be like tapping a perfectly balanced spinning top, a tiny intervention with potentially irreversible consequences. The ethical question is clear. Does our right to knowledge extend to altering or even disturbing one of the universe's most unique and stable objects? This is not merely about losing a data point. It is about the permanent absence of a cosmic wonder that may have existed for billions of years. The principles we develop now will set a precedent for all future exploration, establishing a thoughtful approach for how an intelligent species interacts with the fundamental workings of the cosmos. How do we weigh the immense value of pure understanding against the potential cost of our interference? This question leads us to a final, deeply personal reflection on what this entire journey means for us, not just as scientists, but as conscious beings finding our place in a vast and mysterious universe. A star's quiet defiance against the void mirrors our own deepest hopes. We look up and see not just points of light, but stories of endurance that resonate across the immense distances. Every human culture has found meaning in the stars, weaving them into myths and navigation charts, using their steady presence to mark time and inspire art. The star that refuses to fade becomes a new kind of celestial story, one that speaks directly to our own experiences of perseverance. In its lasting stability, we find a cosmic metaphor for resilience, for the ability to find balance against forces that seek to pull us apart. This connection transforms abstract physics into something deeply personal. How does the light from a star billions of years old, one that surpassed its expected fate, change the way we see our own challenges here on Earth? It invites a shift in perspective, where our personal journeys are cast against a backdrop of cosmic endurance. The same curiosity that drives an astrophysicist to model a quark star also drives a poet to write about light enduring in the dark. This shared sense of wonder is what binds the scientific and the artistic, two different ways of seeking truth in the universe. Contemplating these celestial survivors fosters a profound appreciation for the unknown, not as something to be feared, but as a source of endless inspiration. It reminds us that mystery is not a barrier to understanding, but the very reason we continue to look up and ask questions. Our journey to comprehend these stars is, in its own way, a reflection of their own story, a persistent search for light and stability in a vast and often overwhelming cosmos. This introspective moment grounds the entire cosmic mystery, linking the fate of distant suns to the human spirit's timeless urge to explore and endure. These stellar survivors rewrite the cosmic rules right before our eyes. We have journeyed through the strange physics that allows a fading star to stand firm, from the quantum pressure that forms an unbreakable support to the incredible spin that builds a wall against gravity. We have considered exotic matter transforming at the core and the possible influence of invisible dark matter. Each of these forces represents a fundamental piece of the puzzle, challenging the very foundations of what we thought we knew. The Chandrasekhar limit, once a clear boundary, now appears flexible. The whispers of gravitational waves hint at structures we are only beginning to decode. These stars are far more than simple anomalies. They are profound windows into the deepest laws that shape everything from the smallest particle to the grandest galaxy. Their enduring light invites us to see the night sky differently. The next time you gaze upward, remember that some of those points of light are cosmic rebels, holding on against incredible challenges. I would love to hear which of these mysteries captured your imagination. Share your thoughts in the comments below, and if you want to continue exploring the wonders of space, subscribe for more journeys into the unknown. Our shared curiosity is what pushes the boundaries of discovery, reminding us that the universe is always ready to reveal its next great secret to those who dare to look.